तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the last lecture we have seen about composition of relations. We have also seen what is a power of a relation. So, if R1 is a relation on A cross B and R2 is a relation on B cross C, then R1 R2 we can define on A cross C from A to C. Now, if R is a relation, binary relation on A, that is A cross A, then you can talk about the power of R. R power 0 is the equality relation, R power 1 is R and R power 2 is R into R. Because of the associative property of composition of relation, we can say without any ambiguity R power n plus 1 is R power n into R. Now, we have also seen that R power m into R power n is R power m plus n and R power m n is equal to R power mn. These things also we have seen. We consider one example also. Let us consider one more example. Take a relation on a set A consisting of 4 elements A, B, C, D, and R is defined like this by a directed graph A, B, C, D. This is the relation. So, R consists of the pairs A, B, B, A, B, C and C, D. A, B, B, A, B, C, C, D. Now, what is R power 0? R power 0 is the equality relation on this set. So, that can be represented by the diagram like this. It consists of the pairs AA, BB, CC and PD, and R power 1 is R. Now, what can you say about R squared and R cubed? I shall use this. R squared can be represented by the diagram like this. If there is a path of length 2, that will be replaced by a single arc in R squared. So, A to B, B to A you have. So, there will be a self loop here. B to A to B is there. So, there will be a self loop here. And A to B, B to C is there. So, A to C, there will be an arc. B to C, C to D, there is an arc. So, B to D, there will be an arc. This is R squared. Then R cubed will consist of all paths of length 3 replaced by a single arc. So, what is R cubed? If you write like this, a path of length 3 will be replaced by a single arc. So, R cube will consist of an arc representing a path of length 3 in R. R is this. So, A to B, B to A to B. There is a path of length 3 here. So, it is like this. Then B to A to B, B to A, there is a path of length 3. So, there will be an arc like this. B to A to B, B to C, there is a path of length 3 here. So, it will be like this. Then A to B, B to C, C to D, there is a path of length 3. So, there will be an arc like this. This is R cubed. Now, what about R power 4? Okay. So, I shall write here R power 4. Let us see what are the arcs representing R power 4. Maybe this we can write. R power 4, if you take any path of length 4 should be replaced by a single arc here. 1, 2, 3, 4. So, there will be a self loop here. 1, 2, 3, 4. So, there will be a self loop here. 1, 2, 3, 4. So, there will be an arc like this. 1, 2, 3, 4. So, there will be an arc from B to. So, you will find that R power 4 is the same as R squared. So, R 5 will be the same as R cubed. So, in this case you find that R 0 represents the equality relation, R 1 represents the given relation, R squared you have found, R cubed, and R power 4 is the same as R squared, and R power 5 is the same as R cubed. So, R power 6 will be the same as this, and R power 7 will be the same as this. So, after some time the pattern repeats, you do not have any more different relations, but the powers will represent already existing relations. So, we have this result. If A is a finite set with n elements and R is a relation on A, then there exists S and T such that R power S is equal to R power T for some S and T between 0 and 2 power n squared. For 2 values S and T, R power S will be equal to R power T. If the underlying set A consists of n elements, R is a relation on A and A has n elements where n is a finite number. Why this? Because if A has n elements, what is the maximum number of ordered pair you can have on A cross A? N squared. N squared elements you can have on A cross A. A cross A will have n squared elements. And any relation on A or rather A cross A can include each one of them or can exclude each one of them. So, possibly you can have 2 power n squared distinct relation on A, because each one of this, if you look at it as a graph, each one of the arc may be present in the relation or not present in the relation, and maximum you are having n squared arcs. So, possibly totally you can have 2 power n squared distinct relations on distinct relations on A cross E. This includes the universal relation where you have all the elements present, all the ordered pairs present, and the empty relation where you do not have any of the ordered pairs present. So, looking at that way, you see that if you take R0, R1, R2 like that up to R power 2 power n squared, in this sequence you are having 2 power n squared plus 1 element, but maximum you can have 2 power n squared distinct relation on A cross A. So, sum of them should be equal, at least for some values of S and T they should be equal. So, therefore, there will be some S and there will be some T such that R power S is equal to R power T between these values. Okay. That is what is meant by this result. A is a finite set with n elements and R is a relation on A, then there exists S and C such that R power S is equal to R power T and S and T lie between 0 and 2 power n square. We can also look at another example where this can be made use of. Look at this relation. With 8 elements A, B, C, D, E, F, G, H. A relation is represented by this R. Now, find smallest m and n such that R power m is equal to R power n, m less than n. This, how will you tackle this problem? In the last class we have seen that if you take R like this, R power 0 is the equality relation, R is this, R squared is this, then R cubed will again be the equality relation, because each path of length will be replaced by a loop. If you take the first component alone, the relation consists of 2 components. The first component repeats after 3 steps. R0 will be equal to R cubed. I will call this as R1 and R2. So, R1 will repeat after 3 steps. Now, the same argument you can use for the second component also. R20 will be the equality relation and R21 will be this, R22 will be every path of length 2 will be replaced by an arc, R3 will be every path of length 3 will be replaced by an arc, R4 every path of length 4 will be replaced by an arc, R5 will be every path of length 5 will be replaced by an arc. If you follow the same argument as the earlier case, you will find that R21, R22, R23, R24 will be different, but when you consider R25, R20 will be equal to R25 equal to R210 and so on. So, the first component will repeat after every 3 steps, the second component will repeat after every 5 steps. For the relation to be the same, both the components have to repeat, both the components have to repeat in the same manner. So, you will find that after 15 steps, this will be the same and this will also repeat after 15 steps, 3 and 5. This repeats every 3 steps, this repeats every 5 steps. So, taking the LCM of 3 and 5, after 15 steps, the whole thing will get repeated. So, the m and n smallest m and n such that r power m is equal to r power n, where m is less than n will be, the answer will be m is equal to 0, the equality relation, and n is equal to 15. This also will be the equality relation on this. So, you get r power 0 is equal to r power 15. Let us look at a small result on this power of R. Let R be a binary relation on a set A, and suppose that R power S is equal to R power T for some S and T with S less than T. Before proceeding to that, I want to mention one more point, that R power S becomes equal to R power T only if A is a finite set with n elements. If A is an infinite set, this may not be true at all. For example, let us consider the relation on the set of non-negative integers. The underlying set is a set of non-negative integers 0, 1, 2, etc. And the relation is R is represented like this, x is related to y if y is equal to x plus 1. So, what is R squared? R squared will be represent R squared y if y is equal to x plus 2, and any R power s will be x R power s y if y is equal to x plus s. Let us consider this situation in a graphical manner. So, the set of natural numbers you can represent like this. R will be represented by this. A is related to B if A is B is equal to A plus 1, right. So, R power S will be denoted by 0 will be related to S, 1 will be related to S plus 1, and so on. So, if A is related by R power S to B, then B will be A plus S. In this case, you find that none of the R's are equivalent, R power 0, R power 1, R power 2, etc. They are all different. So, the result which you had for finite set like this will not hold when A is an infinite set. When A is a finite set, we had this result. This will not hold when A is an infinite set. That is what we have considered now. Let us consider one more result about the power of a relation. Let R be a binary relation on a set A, and suppose R power S is equal to R power T for some S and T, where S and T are integers and S is less than T. Let P be equal to T minus S, then R power S plus K is equal to R power T plus K for all K greater than or equal to 0. R power S plus Kp plus I is equal to R power S plus I for all Ki greater than or equal to 0. And there is a third result. Let S be equal to R power 0, R power 1, R power 2, etc. up to R power T minus 1. Then every power of R is an element of the set S. That is, if you have R power Q belonging to, if you have any R power Q, it will belong to S for all Q belonging to N. Let us prove one by one. First, let us consider the first part. R power S plus K is equal to R power T plus K for all K greater than or equal to 0. So, this is what we want to prove. We know that R power S is equal to R power T. We have to show that R power S plus K is equal to R power T plus K for all K greater than or equal to 0. Use induction. Basis class K is equal to 0, you know that r power s is equal to r power t, k is equal to 1, r power s into r equal to r power t into r. So, you are combining with r, you are concatenating with r. So, this will be r power s plus 1 equal to r power t plus 1. Then the induction portion is like this. Assume r power s plus I equal to r power t plus I. To prove r power s plus I plus 1 equal to r power t plus I plus 1. You know that this is equal to r power s plus I into r, and because r power s plus I is equal to r power t plus I, you can write it like this, and this is nothing but r power t plus I plus 1. So, r power s plus k is equal to r power t plus k for all k greater than or equal to 1. Next, we have to take the second portion, that is r power s plus k p plus I is equal to r power s plus I for all k I greater than or equal to 0. R power s plus k p plus I is equal to r power s plus I for all k I greater than or equal to 0. Here again you can make use of induction where p is t minus s, p is defined as t minus s. Now, from the previous result, if you prove r plus kp is equal to r power s, then I can vary by adding I on both sides, you can say that they are equal, there is no problem. So, what you want to show is r power s plus kp is equal to r power s. If k is equal to 0, r power s is equal to r power, k is equal to 0, r power s is equal to r power s, you get. K is equal to 1, r power s plus p, that is equal to r power s, p is t minus s equal to r power t, but we know that r power t is r power s. So, this is somewhat like a basis class of the induction, and you can show that use induction again, use induction portion. Suppose r power s plus kp equal to r power s, suppose, then r power s plus k plus 1p equal to r power s plus kp plus p equal to, what is r power k plus s, this is r power s plus k, r power s plus kp r power p, but what is p? R power s plus kp is r power s, r power p is t minus s. So, this is equal to r power s plus t minus s equal to r power t, and we know that by assumption r power t is r power s. So, we can prove in this manner that for any k and I, again if you multiply this by r power I and multiply this by r power I, that plus I will, you will get. So, for any k and I greater than or equal to, you can show that r power s plus kp plus I is equal to r power s plus I. Now, let us come to the third part. What is the third part? Let s is equal to r power 0, r power 1, r power 2, r power t minus 1. Then for any power of r, you can say that r power q belongs to s for all q belonging to n. So, for any power, any q which is a natural number, r power q belongs to s, where s is defined as r0, R1 up to R power t minus 1. What we already have is R power t is equal to R power s, right? And the previous two results we have already proved. Now, there are two possibilities. Take q belonging to n, q is any natural number. Then if q is less than t, if q is less than t, obviously it is in this, R power q will be in this set. So, that is okay. If q is less than t, R power q is in this set, so the result is proved. But if q is greater than t, greater than or equal to t, what happens? Then you write q as s plus kp plus I. You can write q as s plus kp plus I. How is it is possible? First from q you subtract s, okay. Then whatever is remaining divide by p as much as possible, where k is the quotient and I is the remainder. So, what can you say about I? I will be less than p, it is the remainder, you are dividing by p. So, I is less than p, or what is p? That is I is less than t minus s. So, any q, if it is greater than or equal to t, you can write it in this form, s plus kp plus I. Where, how do you get this? From q subtract s you get q dash, and divide this q dash by p, you get k as the quotient and I as the remainder. Now, by the second result, we know that R power s plus kp plus I is equal to R power s plus I for all k and I. This we know from the previous result. Okay. So, R power q, if you write it as R power s plus kp plus I, it will be equal to R power s plus I. In this case, when q is greater than or equal to t, you can write it as R power s plus I, where I is less than t minus I. Now, I is less than t minus s, so s plus I will be less than t. So, this s plus I is less than t. So, R power s plus I, because s plus I is less than t, it will belong to one of these, it will be one of these elements. So, R power s plus I, that will belong to s. Okay. So, we have considered both the cases when q is less than t and q is greater than or equal to t. By q, when q is less than t, by definition itself it will belong to this set, but when q is greater than or equal to t, you express it in the form, you express q in the form s plus kp plus I, so that R power q becomes equal to R power s plus I, and so s plus I is less than t. So, this will be one of the elements here and belong to s. So, this proves the result. So, these are some results about powers of R. The point to remember is, if you represent it as a directed graph, if you represent R by a directed graph, then R power n will consist of the directed graph, where every path of length n in R is replaced by a single arc. This is what you have to remember. Next, we shall study about some closure. We have seen what is meant by a relation to be reflexive, to be symmetric, to be transitive, and so on. We shall see what is meant by a reflexive closure, symmetric closure and transitive closure. why is it necessary to study this? For example, you may have a communication network in which there is direct link between A, B, there is direct link between B and C, and there is direct link between C and D, but there is no direct link between A and D or B and D or A and C. Now, I want to find out from which nodes I can direct a message to which node. See, there is a direct link between A and B, but and also there is a direct link between B and C. So, I can route a message from A to C. So, I want to find out all the pairs of nodes where from the first node I can route a message to the second node. This in essence will be finding the transitive closure of this relation. Okay. So, let us see what is meant by reflexive closure, symmetric closure and transitive closure. Let R be a binary relation on a set A. The reflexive, similarly we will study symmetric and transitive, but first we will see reflexive. The reflexive closure of R is the relation R dash such that R dash is reflexive, R dash contains R. For any reflexive relation R2 dash, if R2 dash contains R, then R2 dash contains R dash. This is the definition of reflexive closure. Similarly, for symmetric closure, you have to read like this. If R is a binary relation on A, the symmetric closure of R is the relation R dash such that R dash is symmetric, R dash contains R. For any symmetric relation R2 dash, if R2 dash contains R, then R2 dash contains R dash. Similarly, for transitive closure you have to read like this. Let R be a binary relation on a set A. The transitive closure of R is the relation R dash such that R dash is transitive, R dash contains R. For any transitive relation R2 dash, if R2 dash contains R, then R2 dash contains R dash. So, the reflexive closure of a relation R is the smallest reflexive relation containing R. The symmetric closure of R is the smallest symmetric relation containing R. The transitive closure of R is the smallest transitive relation containing R. We will denote the reflexive closure by RR, symmetric closure by SR and the transitive closure by TR. So, the reflexive closure is denoted by RR, the symmetric closure is denoted by SR and the transitive closure is denoted by TR. Okay. In a crude way or a very naive way, you can define like this. Let R be a binary relation and you can represent by a graph, a directed graph. R can be represented by a directed graph, some graph. Now, what is the, it may have some self loops, it may not have all self loops, but it may have some self loops. Now, the reflexive closure of R is the smallest reflexive relation containing R. That means, you should add self loops wherever it is not there. You should add the self loops so that it becomes reflexive. It amounts to this, finding the reflexive closure amounts to this. Now, what about the transitive closure, symmetric closure? So, if there is an arc in one direction between two nodes, the symmetric closure should also have the other arc in this direction. So, when you want to find the symmetric closure of R, if there are two arcs like this direct in both directions between two nodes, it is okay. If there are no arcs between two nodes, then also it is okay. But if between two nodes, if you have one arc pointed like this, you must add the arcs in the other direction also to make it symmetric. So, try to add the minimum number of arcs to make it symmetric, and that gives you the transitive symmetric closure. Now, what about the transitive closure? The transitive closure is if there is a path of length if there is a path between two nodes, directed path between two nodes, you must also add this arc. If there is a path here, you must add this arc. So, try to add the minimum number of such arcs so that you get the transitive closure. The transitive property means that if there is a path between two nodes, then there should also be an arc between the two nodes. So, that transitive property, if it does not hold, you have to make it hold. So, whenever you have a directed path between two nodes, you must also try to add the arc corresponding to that. So, this is putting it in a simple manner. Let us study some properties. Before that, let us consider some relation on the set of non-negative integers n. Look at the less than relation. What can you say about the reflexive closure of the less than relation? Less than relation is not reflexive. X is not less than x, so there will not be any self loops. So, if you look at the natural numbers like this, less than relation will have a is less than b, a is less than 0, 1, 2, like that you will have arcs a is less than c and so on, but there will not be any self loop. The reflexive closure should have self loop at every node, and so the reflexive closure of less than relation will be the less than or equal to relation, including this, like this, self loops like this. What can you say about the reflexive closure of the equal to relation? It is already reflexive, so that will be equal to the reflexive closure of the not equal to relation. It is two elements are directed. There is a direct arc between two integers if they are not the same. You must also add self loops at every point. You must add the equality relation, that will become equal to the universal relation, where every number is connected to every other number. So, this is something about reflexive relation. Let us see about the reflexive, more about reflexive closure. Now, this you can very easily see. Let R be a binary relation on the set A, then R is reflexive if and only if the reflexive closure of R is equal to R. R is symmetric if and only if the symmetric closure of R is equal to R. R is transitive if and only if the transitive closure of R is equal to R. Let us take the first one and prove. Let the reflexive closure of R be R dash. Now, if R is already reflexive, R satisfies if R is reflexive, it satisfies all the conditions mentioned in the definition of the reflexive closure. It is a reflexive. What is the reflexive closure? It is the smallest reflexive relation containing R. If R itself is reflexive, then it is reflexive, it contains R, and any other reflexive relation will contain this. All the three conditions are satisfied. So, if R is reflexive, R will be just the reflexive closure will be R itself. Similarly, if R is symmetric, the smallest symmetric relation containing R will be itself, R itself. So, that is why these results follow. It is not very difficult to see these results. Let R be a binary relation on a set A, then the reflexive closure of R is R union E. This is what we have already seen. The reflexive closure of less than is less than or equal to and so on. So, we want to show that R is a binary relation on A, then the reflexive closure of R is R union E. That is, as a graph we are adding self loops wherever you want. How do you prove that? Let the reflexive closure of R be R dash. Okay. Then the three conditions it has to satisfy. R dash should contain, R dash is reflexive, R dash contains R, and if R2 dash is any other reflexive relation containing R, then R2 dash contains R dash. This is the definition. Now, you can see that when you take R union E, it is reflexive because it contains E, it is reflexive. It contains R, that is also satisfied. Now, we have to only consider the third portion. If R2 dash is any reflexive relation, I will write this. If R2 dash is any other reflexive relation containing R, then R2 dash should contain this R union E. This can be easily proved. Suppose xy belongs to R union E, R union E. Okay, I shall write here. Suppose xy belongs to R union E. There are two possibilities. One is xy belongs to R, or xy belongs to E. And this case it will be actually of the form xx. E means it will be of the form xx. Now, if xy belongs to R, xy will belong to R2 dash. The reason is R2 dash contains R. By the way we have taken R2 dash contains R, so xy will belong to R2 dash also. Now, if it belongs to E, it is of this form, then also it will belong to R2 dash. The reason is R2 dash is reflexive. R2 dash is reflexive. So, it will contain all pairs of the form x x. So, whenever xy belongs to R union E, it also belongs to R2 dash. That means R2 dash contains R union E. So, it satisfies all the three conditions mentioned in the definition of the reflexive closure, and so we find that the reflexive closure of a binary relation R is given by R union E, where E is the equality relation. R is the given relation and E is the equality relation. Next, we shall go to symmetric closure. Again, let us consider some examples. As I mentioned earlier, in a symmetric closure, if you represent it as a graph, if you have an arc in one direction, you must also add the arc in the other direction. So, let us consider the set of natural numbers or non-negative integers 0, 1, 2, 3, 4, etc. This is 0, 1, 2, etc. What is the symmetric closure of the less than relation? A is less than B then you must also add the arc the other way round. So, the symmetric closure of less than relation will be the not equal to relation, and the symmetric closure of equal to relation is equal to, and the symmetric closure of less than or equal to relation is the universal relation. Because equal to means no arc between any two nodes, you will not add any more arcs. In the less than or equal to, again if there will be self loops at every node, and also when there is a arc like this, you will also add the other way around. So, that will give you the universal relation on the set of natural numbers. Now, we have to find out how we go about finding the symmetric closure of a binary relation R. For that, we have to know what is meant by the converse of a relation. Let R be a binary relation from A to B. The converse of the relation R, denoted by RC, is the binary relation from B to A, defined as follows. RC is YC, RC consists of ordered pairs YX such that XY belongs to R. So, suppose I have a relation R consists of say 3 pairs x1, y1, x2, y2, x3, y3. RC will consist of y1, x1, y2, x2 and y3, all the order reversed. If D is the digraph of the relation R, the digraph of RC can be considered like this. It can be constructed from D by reversing the direction of all the arcs of D. So, if you represent a binary relation, here we have not even taken the same thing, a binary relation from A to B, there are some elements here. So, the binary relation can be represented like this. The converse, if R is this, what can you say about RC? The arc should be reversed in this. The direction should be reversed. So, it will be on B cross A. It will be on B cross A. Let R be a binary relation. So, RC is the set of ordered pairs YX where XY belongs to R, and if D is a digraph, the RC can be constructed by D by reversing the direction of all the arcs of D. We have some results about converse. R, R1, R2, they are all binary relations from A to B. Then each of the following holds. R power C is equal to R. That is, if you take the converse, you have to reverse the direction of the arcs. Then to take the converse again, you have to again reverse the arcs, so you get back the original relation. R1 union R2 C, the converse of R1 union R2 is the converse of R1 union converse of R2, and similarly this, etc. We shall prove the B part. It says R1 union R2 C is equal to R1 C union R2 C. What does that mean? If XY belongs to R1 union R2 C, this is equivalent to saying YX belongs to R1 union R2, and that is equivalent to saying YX belongs to R1 or Yx belongs to R2, that is equivalent to saying xy belongs to R1C. For Yx belongs to R1, xy will belong to R1C, or here Yx belongs to R2 means xy will belong to R2C, and that is equivalent to saying xy belongs to R1C union R2. So, we get R1 union R2C is equal to R1C union R2C. The converse is denoted like this. The other results can be proved in a similar manner. For intersection also you can prove in a similar manner. This is the whole A cross B denotes the whole Cartesian product from A to B. Taking the converse will be it is the whole Cartesian product from B to A. And the empty relation means there is no arc at all in the represented in the graph. That means you need not have to change the direction of any arc. So, the converse of the empty relation is the empty relation itself. And similarly, the other results follow. R bar C is equal to R C bar and so on, where the R denotes the complement, and R1 minus R2C is R1C minus R2C. If A is equal to B, then R1 R2C is equal to R2C R1C. This you can see like this, A is equal to B. So, R is a binary, R1 and R2 are binary relation on A. So, R1 R2 is represented like this. If there is an arc representing this is R1, this is an arc from R, this is B to C, A comma B belongs to R1, B comma C belongs to R2. Then by our definition AC will belong to R1, R2. Now, B comma A will belong to R1C, C comma B will belong to R2C. If you reverse the directions, C comma B will belong to R2C, B comma A will belong to R1C. Now, what about an element belonging to R1, R2C? CA belongs to R1, R2, C, and this you can get by combining CB and BA. By combining CB and BA, CB and BA you can get. That is, if you combine CB and BA, you get CA, and this belongs to R2C and this belongs to R1C. So, you get that R1 R2C you can get by combining or by applying the composition operation on R2C and R1C. That is, if you have these two arcs, R1 R2 will contain this arc, and when you see the converse, there will be an arc from here to here, and that you can obtain like this, that is R2 first, R2C and then R1C. The last one is R1, if R1 is contained in R2, then R1C is contained in R2C. It is also not very difficult to see that R is a binary relation on A, then R is symmetric if and only if R is equal to RC. So, whenever you have the ordered pair AB, if you also have the ordered pair BA that is symmetric, that means if it is symmetric means when you have the ordered pair AB, if it is symmetric, if you have AB, you will also have BA belonging to R. If AB belongs to R, BA also will belong to R if it is a symmetric relation. In that case, the converse will have converse of R will have BA, it is also in R. So, RC becomes equal to R. It is not very difficult to see this result. If R is a binary relation, then it is symmetric if and only if R is equal to RC. Of course, you can very easily see that if R is equal to RC, whenever it contains AB, it also contains BA. So, it has to be symmetric. Then we have to also consider what is a symmetric closure, and we find that if R is a relation on a set A, then the symmetric closure is given by R union RC. Let us look into we have to look into the proof of this, and we have to also consider what is meant by a transitive closure and some properties of the transitive closure. We shall consider this in the next lecture.